Hey, what's up, peeps? Now that we've talked a little bit about what the heck a buffer is and how a buffer works, we're going to talk about how we calculate the pH of a buffer system. Now, as you take a look at the example that is on your screen and in your notes, we're going to calculate the pH of a buffer solution that is 0.050 molar in benzoic acid, and we're given the Ka value for benzoic acid, and 0.150 molar in sodium benzoate. All right, so the first thing we want to do is write out the equation that represents this buffer solution. We've got our benzoic acid reacting with water to form hydronium ion and the benzoate ion. Now, if it was just the weak acid, there would not be a whole lot of this benzoate ion, its conjugate base, in solution, because remember, weak acids do not ionize very much. So that's where this information about the sodium benzoate comes into play. We have to add this conjugate base from some other source because it's not going to come from the weak acid. Notice the sodium isn't included. The sodium's a spectator ion. We don't really care about it. Okay, so initially we have 0.05 molar concentration of our weak acid, effectively no hydronium ion because this is a weak acid, and 0.150 molar conjugate base. We're not worried about the water because it's a pure liquid. Again, with a buffer solution, you're going to have both weak acid and conjugate base. Next, let's think about the change. It's going to be minus x plus x plus x. And if you're wondering why it's going to be minus x here and plus x here on this side, think about your Q expression. Think about the conditions that we have initially. Concentration of products over concentrations of reactants. And the value of Q is essentially going to be 0. And so this reaction is going to shift to the right to establish equilibrium. So at equilibrium, our concentrations are going to be 0.050 minus x, x, and 0.150 plus x. The expression for Ka is going to be concentration of products over concentrations of reactants. Again, remember, we're not going to include water because it's a pure liquid. I'm going to plug in my value for Ka and plug in my concentrations that I've defined at equilibrium. We're going to make the x's small approximation because our initial concentration and the Ka differ by a factor of 1,000 or more. Next, we're going to set this up to solve for x. That simplifies our expression, makes it easier to solve. We just jump to our calculator and solve for x. X in this case is going to equal 2.2 times 10 to the minus 5 molar. Then to solve for the pH, we're simply going to plug that hydronium ion concentration into the formula for pH. So pH is equal to the negative log of 2.2 times 10 to the minus 5. Again, we're going to jump to our calculator, take the negative log of 2.2 times 10 to the minus 5. To solve for the pH of this buffer solution, which is 4.66. So essentially, you can solve for the pH of a buffer system very similarly to how you solve for the pH of a weak acid. However, a big difference that you have to watch out for is to recognize that because it's a buffer, you're going to have substantial amount of not only your weak acid, but also your conjugate base. 6.5 second E, negative 5, close parentheses, times 0.05 enter. Divided by 0.150 enter. Negative log second enter. Boom. Okay, now there is another way to solve for the pH of a buffer, and that is simply to recognize, given your equation for your buffer system, recognize that the Ka for that equation is expressed as concentration of products over concentration of reactants. And you can rearrange this equation to solve for the hydronium ion concentration. So the concentration of hydronium ion is equal to the Ka times the concentration of your weak acid over the concentration of the weak base. And this is a really important formula that you need to recognize for all of the buffer calculations. Hydronium ion concentration in general is equal to the Ka times concentration of the weak acid over the concentration of the base. In this example, that means 6.5 times 10 to the minus 5 over the concentration of our weak acid, 0.050, over 0.150, the concentration of our weak base. Quick jump to our calculator, we'll solve for the hydronium ion concentration, which is what we ended up with initially, 2.2 times 10 to the minus 5 molar. Plug that into our equation for pH, which is equal to the negative log of our hydronium ion concentration, and then solve for pH. We get 4.66. Parentheses, 6.5 second E, negative 5, close parentheses, times, new parentheses, 0.050 divided by 0.150, close parentheses, enter. Negative log second enter. Boom, same pH. So In short, for buffers, it's a good idea to recognize how to rearrange the expression for Ka, solve it for hydronium ion concentration, and then simply plug in the concentrations of your weak acid and conjugate base. Done.